Mathematical form of Ohm's law. Voltage across a conductor or a resistor is directly proportional to the current flowing through the resistance. Okay, take a cell of EMF E and connect it to a resistance. Okay, it sends the current and let V be the potential difference across the resistor. If more the potential difference, more the current. Lesser the potential difference, lesser the current. Okay. Yes. If you want to equate it, you have to multiply by a constant. What do you call this constant as? V is equal to. You want to multiply by one constant. What is that constant is called as? What is that constant it's called as? You have to multiply by a constant. V is equal to. R is the constant. You have to multiply. Where R is called as the resistance of the wire. Okay, resistance of the wire. Resistance offered by the wire to the flow of the current. So this is the mathematical form of which law it is? Ohm's law. Okay, this is the mathematical form of Ohm's law. Okay, yes. This is the mathematical form of Ohm's law. So how do you measure the resistance? Therefore, R is equal to, from this equation, R is equal to, come on, R is equal to, R is V by I. Okay, R is equal to V by I. Yes. Okay. What is the unit of resistance? Resistance is measured in ohm. What is the unit of resistance? It is measured in ohm. What is the symbol for ohm? Omega, but we don't call it as a omega. Okay, we just okay, write it as this symbol and we read it as a ohm. Okay, we read it as a ohm. Okay. Yes. Define resistance. When do you say that the resistance is 1 ohm? Okay, define the resistance. What is the resistance? Define resistance. What is the resistance? What exactly the resistance is?
Resistance of the conductor is directly proportional to its length.
It is the amount, it is the amount of opposition offered by the conductor to the flow of electrons, to the flow of current. Okay, it is the opposition to the flow of current. Opposition offered by the conductor to the flow of current. It is the opposition, okay, by the metal or wire to the flow of current is called as resistance. Okay, resistance. Yes. Okay. You know the unit of resistance. You know the unit of resistance. So R is equal to, R is nothing but the resistance. Okay, resistance. Okay, anyhow, instead of resistance, the same word, let's use opposition. Opposition. Okay, opposition to the flow of current. To the flow of electric current in the conductor is measured as a resistance. Good. Resistance depends on two things. Name them. What are the factors on which the resistance depends on? What are the factors on which resistance depends on?
Length and area of cross section.
Yes, the resistance is depends on two things: length of the wire and area of cross section of the wire. Come on, how exactly the resistance depends on the length? How exactly the resistance depends on the length? The resistance of a conductor is
directly proportional to its length.
Okay. Yes, more the length, more the length,
more the current,
more the length,
more the resistance,
more the resistance, more the resistance, more the resistance. Okay. If you double the length, resistance doubles. Triple the length, resistance triples. Halve the length, resistance is halved. Okay. Yes. Next, resistance is inversely proportional to
to the area of cross section.
Yes, resistance is inversely proportional to the area of a cross section. How can you write that? Mathematically, R is proportional to 1 by A. The resistance is proportional to 1 by A. Combining these two equations, combine these two equations and you can just write its R is proportional to L by a. Okay, this proportionality, okay, proportion can be equated by multiplying a constant of proportion. Multiplying a constant of proportion. What is the constant of proportion? Generally, you choose here. Resistance is equal to, resistance is equal to
1 by A.
what is the name given to this constant?
Rho.
Rho is called as, that's the symbol. So rho is called as resistivity. It's called as resistivity. Rho is called as resistivity. Rho is called as resistivity. Resistivity, it do not depend upon the length. Okay, it's do not depend on length, and also it do not depend upon area of a cross section. Do not depend on length or do not depend upon the area of a cross section. Do not depend on length or area of cross section. What is the reason? Cross multiply this and solve this for solve this for resistivity. Rho is equal to rho is equal to rho is equal to rho is equal to, come on. So
RA by L.
yes, resistance into area of cross section divided by a L. Okay, now define resistivity of a material. Resistivity is applicable for material. Resistivity of a copper, resistivity of an iron wire, resistivity of nichrome wire. Now can you define resistivity? Define resistivity. Define resistivity. How do you define resistivity? By using the above equation. So resistivity is equal to resistance of a wire having a 1 meter square area of cross section and 1 meter length. When A is 1, L is 1, rho becomes R. Come on, tell me. So define the resistivity. Define resistivity of a wire. Resistivity is numerically equal to resistance of a wire having
1
area of cross section
1 meter square.
and length
1 meter.
1 meter. Okay. Now, so now we have to solve the unit for resistivity. Okay. How do you find the unit for resistivity? Unit for resistivity. Okay. Unit for resistivity. The equation is R rho is equal to R into A by a L. R is measured in ohm. Okay. And area is measured in
Length.
area is measured in area is measured in meter square.
Meter square.
What is the unit of area?
Meter. Meter square.
Meter square. Unit of length?
M.
M. Cancel this and can you tell what is the unit of resistivity? What is the unit of resistivity?
M.
Quickly. Ohm?
M. Into M.
M. Meter.
Meter.
So, ohm meter. Okay, ohm meter. Okay. Ohm meter. What is the unit of resistivity?
Ohm meter.
What is the unit of resistivity? Ohm meter. But in CGS unit, sometimes it may also use the word ohm centimeter. Okay, ohm centimeter. Yes. Okay. Now, resistivity. Resistivity is a constant for a given material, but it also depends on some quantities. Resistivity is found to depend on. Resistivity depends on. Resistivity is found to depend. Okay, depends on. Number one. What is that? It depends on the nature of the
Material of the conductor.
Yes, nature of material. That means whether it is a copper, iron, aluminium, okay, nichrome, okay, like that. But copper, it is constant. Copper resistivity do not change. But provided temperature should not be changed. Always temperature at room temperature only should measure. So hence resistivity depends on the nature of material and also depends on the temperature. It also depends on the temperature. It also depends on temperature and presence of impurities. Whether it is a pure metal or alloy. Alloys generally have a higher resistance and higher resistivity. We can say whether it is a impure or a pure. Okay, impurities, presence of impurities in the metal. So always you should take a pure substance, have a lesser resistivity. Okay, if the metal used in the circuits are not pure, its resistance will be high and unnecessarily more heat is produced. Okay, if you buy anything cheap electronic gadgets, they unnecessarily get heated up because the circuit, okay, so circuits what they have used of not good quality material. Okay, yes, cheap phones get heated up faster because of impurities present in their components. Does the iPhone get heated up quickly on using? Maybe while playing games, but normal usage it doesn't get heated up because it is made up of a good quality material. So now you have to use another technical term called as current density. Define current density. Define current density.
Current density is defined as per unit area taken normal to the direction of current.
Define current density. Current density is defined as the.
Per unit
We begin from here. Current density is defined as.
electric current per unit area taken normal to the direction of current.
Yes, electric current per unit area. Okay, unit area. Okay, unit area. The unit area should be cross section. It should be perpendicular to the direction of the current. What is the symbol they have used to define the current density?
J is equal to 1 by A.
Yes, J is equal to
A 1 I by A.
I by A. Current, you only told current. Okay, current density is equal to current divided by area of cross section. Okay, it will be current per unit area. So come on, tell the unit of current density. Current density, numerator ampere, denominator
Ampere per meter.
meter square. Denominator area is measured in a meter square. Okay. Yes. Define the term current density. Current density is nothing but the electric current per unit area taken normal to the. That means the area. The area is taken normal. What's the meaning of it? I can take the wire carrying the current. One cross section area you should take perpendicular to it. Perpendicular to it, and through this, okay, how many coulomb, how many amperes of current is passing, okay, divided by the area. That's called as current density. Okay. Oh, what is that? Any problem? No. Meter square. Ampere denominator. Yes, that's good thinking. Correct. This is not ampere. This is not ampere meter square. It is ampere per meter square. Ampere per meter square. Okay. Yes. So ampere per meter square. So ampere per meter square. Okay. Next. Is it a vector quantity? Yes, it has a vector quantity. Why do you think it has a vector quantity? Current is a scalar, but I think this area is there. No? Area we have to take in a particular direction. The cross section area is perpendicular to the direction of the current. That's why it becomes a vector quantity. Okay. Yes. Now let's, after learning the current density, let's learn another
Electrical conductivity.
another new unit called as electrical conductivity. Good. What is meant by electrical conductivity? Okay. Electrical conductivity. Okay. Conductivity. Okay. Yes. Define electrical conductivity. It is the ability of the conductor to conduct the current. Higher the conductivity, more current flows through it. Okay. How do you measure it? What is the symbol to be used? Electrical conductivity is measured by the sigma. Okay. It is measured by the sigma. Actually, it is the reciprocal of the resistivity. It is the reciprocal of resistivity. Conductivity is the reciprocal of resistivity. It is the reciprocal of resistivity. Conductivity is the reciprocal of the resistivity. Okay. Yes. What does the electrical conductivity indicates? It indicates the ability to of the conductors to conduct the current. How do you measure? We are going to derive and show that. Okay. It is measured by the ratio of the current density. Current density divided by unit electric field or electric field. Okay. Yes, give the equation to measure the electrical conductivity. Current density divided by
Electrical field.
electric field. Okay, electric field you have studied in electrostatics, but here what is the meaning of electrical field? Okay, what is the meaning of electrical field in okay, current electricity? For example, take a wire. Let the potential difference from one end of the wire to the another end is V. Let its length be L. Let its length be L. We define a electric intensity because one end is connected to positive terminal, another end is connected to negative terminal. Okay, electric intensity E is equal to V by L. V by L. Potential difference per unit length. Okay, what is E by L stands for? Potential difference per potential difference per unit length. Potential difference per unit length, okay, is called as electrical conductivity. Okay, hence, what exactly we are learning? Electrical conductivity. Okay, represented by the letter, by the symbol sigma. This letter is called as a sigma. It is the reciprocal of resistivity. Okay, in the derivation we are going to show that okay, this electrical conductivity is nothing but the ratio of current density by electric field. Current density per unit electric field. If there is 1 volt potential difference, okay, if 1 volt is the potential difference between the wire of length 1 meter, we call it as E is equal to 1 volt per meter. At that time, this conductivity, electrical conductivity is nothing but just current density. Current density by a 1 volt per meter. Yes. Okay. So now just let's learn another technical term called as relaxation time of the electrons on the conducting metal. What do you mean by relaxation time? Relaxation time. In a metal, take a metal, you know that if one end of the so metal is connected to positive terminal, another end is connected to negative terminal. The electrons are attracted. The electrons are attracted towards the positively charged plate, but they cannot go straight because they'll collide with the atoms and then finally they drift towards. Okay, it is called as drifting. Finally, they drift towards the positively charged plate. So the motion of the electrons under the electric field is not smooth. They have to collide with the atoms. During the collisions, they change the direction. But there is a net movement of all the electrons from negative field to the positive field. Okay, so net movement from negative field to the positive field. Okay, so this type of motion is called as electron drift. Okay, so here they define a one technical term called as relaxation time. Okay, it's called as a relaxation time. The relaxation time is represented by a letter tau. Okay, it is how we have to write tau. Okay, tau, or just like this, tau. Okay, this is how we have to write tau. Okay, tau. Yes. So define tau, relaxation time. Relaxation time is the average time between the two successive collisions. Average time between two successive collisions. Average time between two.
Successive collision.
Okay, between two collisions, there will be different times it will take, but add all the timings and divide by the total number of collisions, that will give an average the time. Yes. What is the textbook says? What's when the relaxation time?
The conducting of a metal is directly proportional.
The conducting means conductivity of a metal is directly proportional to the relaxation time. Okay, directly proportional. Okay, yes, conductivity. Larger the relaxation time. Okay, it depends on, but we can't say now itself whether it is directly proportional or inversely proportion. Okay, relaxation time. So derive a relation between current density J and
conductivity of a conductor.
yes, conductivity is represented by letter sigma. Okay. Yes. Now take a conductor. Conductors are thin, but for the sake of derivation, I have written into some big sized conductor, and connect this conductor to a cell. Cell. Let V be the potential difference across the conductor. Let L be the distance from one end to the another end. One end to the another end. Now, according to Ohm's law, let I be the current flowing through it. Let R be the resistance of the metal. Let R be the resistance of the metal. Okay. Yes. Let R be the resistance of the metal. Okay. Yes. Now, according to Ohm's law, V is equal to. According to Ohm's law, the potential difference is related to the current passing through the conductor as V is equal to. Therefore, I is equal to.
V by R.
I is equal to V by R. But already we know that R can be written as resistance. It depends on the resistivity by using the equation R is equal to rho into L by A. Okay. Yes. Now replace instead of R this equation. So V divided by instead of R rho into L divided by A. And simplify this. I is equal to, the A goes to numerator, V and rho and L and into A. Now this physical quantity, right. Now cross multiply this area of cross section to the left hand side. So I by A is equal to, so I by A is equal to 1 by rho into V by L. Okay. So what is the current by area of cross section? Let A be the area of cross section of this wire. Okay. Yes. What is the technical term I have to replace? Current by area. J is called as current density. Current density is equal to 1 by rho. Okay. Already we have just learned that electric intensity is nothing but V by L. Electric field, not intensity. Electric intensity is equal to V by L. Okay, V by L. So hence instead of V by L, I will write a E. Okay. And by the definition, 1 by rho is nothing but the reciprocal of resistivity is written as conductivity. So hence J is equal to current density is equal to conductivity into electric field. Electric field. So, yes, here electric field, you know that it is from positive field to the negative field, and J is also a current density is a vector. That direction is same as the electric field direction. So, hence, you can say that the current density is related to conductivity into electric field. Conductivity to electric field. This is the relation between current density and electric field, or current density and conductivity and electric field. Electric field. Electric field mainly we have learned in electrostatics, but what is the meaning of electric field? So conductors, it has been explained that electric field is nothing but the the ratio of the potential difference across the ends of a conductor divided by the length of the conductor. Potential difference per unit length is called as electric field. That's the derivation. Take a wire and connect it to a positive and a negative terminal of a battery. As just we have learned that it is not easy for the electrons to move from negatively charged end to the positively charged end, or negative terminal to the positive terminal. The electrons suffers a collision between the atoms. For under each collision, there exists a change in direction. There is a change in direction. So, but somehow the electrons move towards negative field to the positive field. This type of the zigzag motion of an electron, is called as electron drift. Electron drift. Electron drift. So here let's define what is meant by a drift velocity. What is meant by drift velocity? Drift velocity. Drift velocity is nothing but the average velocity. Average velocity. Average velocity. Average velocity. With which the free electrons move from negative terminal to the positive end of a conductor. So under the influence of an electric field. What do you mean by electric field? Inside a metal there exists an electric field in the direction from negative end to the positive terminal. How do you measure? We know that already. The E is measured as a potential difference between the length of the conductor. Between the length of the conductor. Now let's learn the derivation. Derive an expression for drift velocity. So derive an equation for drift velocity. Drift velocity. So for drift velocity. Derive an equation for drift velocity. Yes, again consider a conductor. Consider a conductor. Consider a conductor. So conductor means a metallic wire. Metallic wires are very thin, but for derivation purpose we have written it is of the big size. Now so electric field is always from positive direction to the negative direction. This is the direction of electric field. Under the electric field the electrons move from left to right. Electrons move from left to right. Let the velocity, drift velocity of the electron be Vd. 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 Now, Vd. In electrostatics, we have learned that if E is the electric field at a point and E is the charge on the particle, E is the charge on the electron, then force experienced by the electron is given by E into E, where small e is the charge of the electron and capital E is the electric field. Okay, if E is the electric field, let's assume the electric field is uniform everywhere inside the conductor, and the force experienced by a single electron is given by the charge times the electric field. Okay, electric field. But in classical mechanics, if we have already learned that if m is the mass of the electron and a is the acceleration of its motion, under an electric field, the electrons get accelerated. That means it is not moving with the constant velocity, it's moving with the increased velocity. Let a be the acceleration of the electron. Then, according to the Newton's second law, the force on the electron is also represented as m into a. So one is electric force, and that electric force E is can also be written as it is equal to ma. Therefore, both are represent the same equation of the force on the electrons. So hence you can say that these forces are equal. Before that, here you can say that the charge on the electron, let it be minus E. The charge on the electron is minus E. Okay, the charge on the electron is minus E, or the force is opposite to electric field. The force is opposite to electric field, therefore let's put the minus sign. Now you can equate these two equations. On equating, you will get MA is equal to minus E by EE. And if you divide mass, you will get EE divided by mass gives the acceleration of the electron. Electrons are moving from negative field to the negative end of the conductor to the positive end with this acceleration. Now, so applying the equations of motions to the movement of the electrons. It is found that when the electrons collide with the atom, its velocity stops. Its final velocity stops. Let its initial velocity be, let its initial velocity be, let's see, its initial velocity be 0, and before it collides, it has a maximum velocity. Let that maximum velocity can be considered as a drift velocity. So hence, by using the equation V is equal to U plus AT, when the electron collides with the atom and its initial velocity becomes 0, final velocity, let us consider as the average velocity, drift velocity. That is 0 plus A into the time. So here, the time taken, average time between the two successive collisions is called as relaxation time. It is represented by tau. So here, the tau is called as the relaxation time. The average time between the two successive collisions, relaxation time. Therefore, from this equation, solve this for Vd. Therefore, V drift velocity is equal to acceleration into relaxation time. Now replace the acceleration expressions just we have derived. So this is nothing but minus E by m into tau, where tau is the relaxation time, the average time between the successive collisions. Yes. So this is the derivation of a drift velocity. Drift velocity is equal to minus E by m into tau. More the mass, lesser the drift velocity. More the electric field, more the drift velocity. Yes. What is the tau here? It is the average time between the two successive collisions in a metal, inside a metal. When the electrons move from negative end to the positive end, it has to collide with the atoms. There is a series of collisions take place. So that's the derivation of the drift velocity. Next, with respect to drift velocity, they use one technical term, another important technical term called as electron mobility. Mobility of an electron. represented by the letter mu. So define electron mobility. Electron mobility. Electron mobility. So define electron mobility. Electron mobility is defined, is expressed by the equation mu. Electron mobility is nothing but drift velocity per unit electric field. Okay, when electric field is 1 Newton per Coulomb, okay, 1 Newton per Coulomb, or it is 1 volt per meter, okay, 1 volt per meter. So whatever the drift velocity is called as electron mobility. So hence electron mobility is drift velocity per unit electric field. How do you measure that? So mu is equal to drift velocity divided by electric field. Okay. Yes. So can you give the SI unit of the electron mobility? Yes, we can give. There's no problem. So drift velocity is meter per second. Meter per second. And electric field is volt per meter. Volt per meter. And if you simplify this, you will get, okay, m minus 1 goes to numerator, it becomes 1 plus 1 meter square. Meter square per volt per second. Okay, yeah. So that's how to derive the unit of electric mobility. Okay. Electric mobility. Yes. Can you define, okay, can you define electric mobility in terms of relaxation time? Yes, you can replace instead of Vd. Instead of Vd. So mu is equal to, what is Vd? Just now we have derived that minus E by, okay, m into tau. Okay. Now whole divided by E. So this E get cancelled. Therefore, electron mobility is equal to minus E by m into tau, relaxation tau. So this is the another equation of electron mobility in terms of relaxation, the time. Okay, relaxation time. Derive an expression for current through a conductor in terms of drift velocity. In terms of drift velocity. So derivation of a current, okay, passing through a wire. Current passing through a wire in terms of drift velocity. In terms of drift velocity. Okay. Yes. Your final expression after derivation should be I is equal to N E A V drift velocity, where N is a constant called as number of electrons per unit volume. What is N stands for? Number of electrons per unit volume of the metal. Take a 1 cm cube of a metal or 1 meter cube of a metal, how many electrons are present in it? That is the number, okay, number density of the electron. Number of electrons per unit volume. Okay, where E is the charge on one electron. You know what's the charge on one electron? 1.602 into 10 to the power of minus 19 coulombs. A is the area of cross section of the, okay, of the conductor. V, we know it is nothing but a drift velocity. It is drift velocity. Drift velocity. Yes. So you have to derive the expression for this equation. I is equal to NEAVD. Okay. Now let us assume. Let's take a conductor. Let's take a conductor of area of cross section A, and area of cross section A. Let this area of cross section be A. Okay. Area of cross section be A. and it is connected to positive and negative terminal of a battery, which drives the current I through the wire. I through the wire. Okay, I through the wire. Let L be the length of the conductor. Okay, length of the conductor. Okay, length of the conductor, and A is the area of cross section of the conductor. And what is N? N is nothing but number of electrons of unit volume. Number of electrons present in unit volume. Number of electrons in unit volume. In unit volume. Yes, unit volume. Number of electrons in unit volume. So let that be N. Now, suppose let's assume that. Okay, let's assume that. Okay, Q is the charge passing this cross section. Take a cross section. Take a cross section. Okay, let Q is the charge passing through this cross section in a time t. In a time t. Then we can find out the expression for Q as Q is nothing but the total charge passing through the cross section is nothing but number of electrons per unit volume into volume of the volume of the conductor. Volume of the conductor can be written as A, okay, area of cross section into length. This is the volume. Number of electrons per unit volume into volume, that gives the total number of electrons present in okay, in this metal. So instead of taking this cross section area, we can just take it at the end. We can take this at the end. Okay, we can take it at this end, red colored. So this red colored end. Okay, let us assume that all the electrons pass through this area of a cross section in a time t. In a time t. So the total charge flowing through the cross section of red colored cross section is number of electrons per unit volume into volume of the wire. What's the volume of the wire? Area of cross section into length, and multiplied by the charge on the electron. So this is the total charge flowing through this area of cross section in the time t. Okay, so therefore we can define current. Current is nothing but the charge flowing through a cross section area in a given time t. Now replace this. Okay, Q is nothing but number of electrons, okay, in a unit volume. In the volume, A into L is NaL, and if E is the charge on one electron and multiply by NaL, AE gives the total charge flowing through the cross section. Okay, divided by the time t. Divided by the time t. Yes. Now we know the relation between drift velocity. What is the drift velocity? Drift velocity is nothing but the distance traveled, average distance traveled by the electrons in a unit time. If this is the time is t, let it write it as a t. So let L be the distance traveled by the let L be the distance traveled by the electrons. Okay, and in the time t, this L by t gives the drift velocity. Therefore, instead of L, okay, cross multiply, you will get Vd into t gives the distance. Give the distance. Therefore, we can replace the distance traveled by the electron in terms of drift velocity. Velocity into time gives the distance traveled by the electron. We have assumed that all the electrons are traveled through this distance L in a time t. In a time t. Therefore, replace L by Vd into t. Therefore, current is equal to N A and write E. Okay, instead of L, you just write Vd, drift velocity into time, into charge on the electron, divided by t. Okay, these t get cancelled. The two t get cancelled. Therefore, your final expression is that current, okay, through the conductor in terms of drift velocity is given by N, A, E, and a VD, where VD is the drift velocity. N is the number of electrons per unit volume, A is the area of cross section, E is the charge on one electron. Okay, this is the derivation of okay, yes, expression for the current passing through a conductor in terms of drift velocity. Now by using this, you can, okay, so you can derive the expression for Ohm's law. So give the proof of Ohm's law. How, okay, Ohm's comes into conclusion about his law. You can give the proof for the Ohm's law by using this equation. Okay, yes. Now what you have to do is, from this equation, substitute the drift velocity. We have already derived drift velocity. Vd is equal to minus E by m into tau. Okay, where that minus is only the direction. So you just take only the quantity, magnitude, take only the magnitude and replace in the expression I. Therefore, I is equal to N A E. Instead of Vd, you can just write minus E by m into tau. So, yes, if you want to simplify, let's simplify this equation and put it in a proper form. It is N E square, okay, N A E square, no problem, N A E square, N A E square E by m into tau. Okay, yes. Now already we have learned that electric field is nothing but potential difference divided by the length of the conductor. Potential difference across the conductor divided by the length of the conductor gives the electric field. Okay, yes. Now wherever E is there, you replace by V by L. So hence the equation becomes, what happens to the equation? I is equal to, what happens to the equation? I is equal to N A E square, okay, by M you can just write, and tau you can write, and instead of that E we can just write V by L. V by L. Okay, yes. Now solve this equation for I, because our final expression should be equal to V is equal to IR. V is equal to IR. Hence solve this equation for V. Okay, so V cross multiply. I think let us bring everything into the left hand side. Okay, we will get yes, we will get I into M into L. Okay, so divided by N A E square tau. Okay, tau is equal to V. Tau is equal to V. Okay, tau is equal to V. Therefore, write it neatly as V is equal to I into remaining all the term M L divided by N A E square tau. It is found that all of these are constants. All of these are constant. Mass of the electron is constant, length of the conductor is constant, number of electrons per unit volume, valence electrons constant, area of cross section, charge on the electron, relaxation time is constant, given temperature. So replace those constant by resistance of the wire. So hence V is equal to I into R, where R is given by this expression. Okay, R is given by this expression. So this is the Ohm's law. So according to Ohm's law, the V is, okay, potential difference across the resistor is directly proportional to the current passing through the wire. Okay, hence we have derived an expression for okay, we have derived an expression to prove the Ohm's law. This is the proof for the Ohm's law.